We all know the force of gravity, also known as the gravitational force, that causes the Earth to move in orbits around the Sun. But have you ever wondered where this force comes from and what is the mechanism behind it? Let's see in this video. In 1687, Sir Isaac Newton, known for his 3 laws of motion, gave a formula that explains the gravitational force. He basically said that if there are 2 masses next to each other, let's call this mass number 1 m1, and let's call this mass number 2. So this is m1 and this is m2. Now, if these 2 masses are placed next to each other, what Newton said is that there will be a force pulling them towards each other. Let's denote it as F. And in 1687, he was able to, discover this force, and the formula for this force F is equal to G multiplied by m1 multiplied by m2 divided by r squared. So what this equation basically says, which was discovered, by Sir Isaac Newton. We all know Newton for his 3 laws of motion: Newton's first law, Newton's second law, and Newton's third law. Okay, what this equation says is that the force created, this is the force of gravity that causes 2 objects to be attracted to each other, to be pulled towards each other. Okay, is a function of G, which is what we know as the gravitational constant. Okay, this is a gravitational constant. Okay, and this is the mass of m1, this is the mass of m2, and r is the distance between the centers of these masses. So on the figure, this would be the distance, or it's the distance between the centers. Now this formula seemed to work among the scientists in Newton's era, and it gave satisfactory results up until Albert Einstein. Now when Albert Einstein came, by the way, one of the most important areas of interest to Albert Einstein was to understand the mechanism behind gravity, to understand the mechanism behind the gravitational force. And the first thing that he did, when he had such an interest, he visited Newton's formula for explaining the gravitational force, and he looked at it and he said, well, I don't like this formula. The reason that I don't like it is that it seems to have no time variable, meaning changing any one of the masses in this formula will directly change the force F. And Albert Einstein was interested in knowing the time of this influence, meaning if you change one of the masses, m1 or m2, right, what is the time that is gonna take for the other mass to be affected by this change? In other words, we know that the sun attracts the Earth, right? We know that the Earth orbits around the sun, okay, moves around the sun in orbit. So let me put this on the schematics. Okay, so we have this is the sun, and this is the Earth moving in orbits around the sun. And what Albert Einstein thought is that using this formula, which is F equals G times m1 times m2 over r squared, right? He said that if I assume that the sun goes to 0, okay, what is the time that is gonna take the Earth, which is situated at a distance r from the sun, to be affected by this removal? Now, the formula for Newton doesn't have any time variable, and it basically says that the moment that you remove the sun, the moment that you remove the other body, which is in this case m2, then the force would go to 0, and at this instant, then the other force that remains will continue straight, because it's no longer going to be attracted to the other mass. Okay, and Albert Einstein really didn't like this, because he thought that there would be some time of influence, right? So it's not that if I increase or decrease one mass, okay, directly the other mass is going to be influenced, because they are at a great distance, right? And so he thought he was interested in knowing more about the time of influence, right? So what he did is that he visited Newton's book, where he explains the gravitational force, which is the one that we put in here. Albert Einstein visited Newton's book to try to understand the mechanism behind his formula, and unfortunately Newton himself declared that there was no mechanism. So Newton, in his book, when he wrote this formula down, he didn't have any mechanism explaining this formula. Okay, and here lies Einstein's interests, okay, in explaining the mechanism behind the gravitational force. What's the mechanism behind the gravitational force? Okay, this was the question asked by Albert Einstein, and this was the question that led to the most important theory, the most beautiful theory in physics, which is the general theory of relativity. So let's see how Albert Einstein thought. Okay, what are the steps that he took in order to arrive finally to the general theory of relativity, and what this theory is and why it is so important. Okay, so Albert Einstein's discovery of the general theory of relativity was based on two important connections. Now, the first connection is the relationship between acceleration and gravity, right? And the second connection is the relationship between acceleration and curvature. Okay, so these two connections led him to discover that there is a relationship between gravity and curvature. Because if there is a relationship between acceleration and gravity, and there is a relationship between acceleration and curvature, then there would be a relationship between gravity and curvature, and this relationship between gravity and curvature led him to discover the general theory of relativity. Very important. So let's start by the first connection, which is the relationship between acceleration and gravity. Very important explanation, very important discovery by Albert Einstein, which is the first connection between acceleration and gravity. Between acceleration and gravity. So what's this connection between acceleration and gravity? Now, Albert Einstein's discovery of this relationship came to him when he was at the patent office at Bern in 1907. He was in a patent office, right? In a patent office at Bern, in a city called Bern. In 1907, when he was sitting at his desk, he described this thought that he had when he was there at Bern. He described this thought as the happiest thought of his life. Okay, so let's see what's the happiest thought of his life. This thought has led Albert Einstein to discover the connection between acceleration and gravity. So happiest thought of Einstein's life. Happiest thought of his life. What's the happiest thought of Albert Einstein's life? So while Einstein was sitting, in his desk in Bern in 1907, he looked at the window and he saw a painter, standing on a ladder, okay, and painting a building in front of him, right? And when he looked at that painter, he thought, if the painter was to free fall in air, if the painter was to fall, right? If the painter was to fall in air, he thought that his acceleration gained while he fell down would cancel the gravitational force, meaning the painter himself would feel weightless. In other words, let me explain this in a more understandable way. Suppose the painter, is this man in here, right? And he is standing on a scale, right? Is standing on a scale that measures, his weight. Okay, so when the scale is fixed and the painter is not in motion, and he goes up to the scale is gonna read a certain, weight. Let's say 1,000, right? Let's say 1,000 newtons. Okay, so this in here is fixed. Okay, and the painter is not in motion. Okay, is not in motion. Now suppose that you have the same system in here, which is made up of the painter and the scale. Suppose that you have the same system and both of them, the painter and the scale, are free falling. Okay, are free falling in air, right? At an acceleration, let's say, of 9.81 meter per second squared, which is the gravity. Okay, so in here, let's say that both of these, the painter and the scale, both of them. Let's consider now that they are both falling down, okay, at an acceleration equal to 9.81 meter per second squared. So what's gonna happen to the scale? What's gonna happen to the weight read by the painter on the scale? It's gonna go to zero. Okay, and here the scale is gonna tell you that the weight is zero. Why is that? Because both of them are falling in free air. So this is why Einstein explained that if I was the painter, from the perspective of the painter, if I was the painter, right, falling in free air, I would feel weightless. And he explained this, if I put a scale below me, okay, if I attach a scale to my feet while I am free falling and I looked at the scale, I would see that my weight is zero. Okay, why? Because the scale is falling with me. And here's the idea that led Einstein to discover that there is that gravity itself can be cancelled out by acceleration. Gravity can be cancelled out by acceleration. In this case, as you can see in here, if both are falling with an acceleration equal to 9.81, gravity is cancelled because now the gravitational force, which is the weight, is 0. Okay. Now, to emphasize this more, he even said that the acceleration is not only capable of cancelling gravity, it's also capable of creating gravity. Okay, and he gave another example where he said that suppose that you are in space. Suppose that you are in space. In space, there is no gravitational field. In space, you feel weightless. Okay, so suppose that you are now in space, okay, feeling weightless. Okay, because in space there is no gravitational field. Okay, so this is yourself weightless in space. And what Einstein said, that if I get a weight, I get a scale in here, right, and I tied it with a rope, right. So if I saw you in space, I got 2 ropes tied to a scale in here, okay, and I drove it up, okay, with a certain acceleration, then even though there is no gravitational field, you are going to sense a force pulling, to sense a force between your feet and the scale, and therefore you are going to read the weight on the scale. Okay, and therefore in this case, acceleration creates the force of gravity. Okay, so in the first case in here, when both of them fall in air, acceleration cancelled gravity. So in here, however, in the second case, if you see a man in space and you get 2 ropes tied to a scale, and you pull you pull these 2 ropes with a certain acceleration upwards, the man in here, he's gonna feel his own weight even though there is no gravitational field. So in here, acceleration creates gravity. So after having this thought, Albert Einstein discovered that gravity is all relative. Gravity is relative. There is a connection between acceleration and gravity, and acceleration can cancel out, and in some cases it can create gravity. Okay, so this led Einstein to discover this relationship, the relationship between gravity and acceleration. Okay, so conclusion number 1 that can be drawn from what we talked about in here, okay, is acceleration is related to gravity. Acceleration and gravity are connected. There is a relationship between gravity and acceleration. Now, the second principle, or the second type of connection that Einstein used before finally concluding with the general theory of relativity, is the connection between acceleration and curvature. Because as I told you earlier, he first discovered the relationship between acceleration and gravity, then the relationship between acceleration and curvature, and then he linked gravity and curvature together to discover the general theory of relativity. So what is the second connection, okay, that Einstein made, which is the acceleration, the relationship between acceleration and curvature? Okay, now this connection can be explained using the following. So I think you've all went to amusement parks and played a game, called the tornado game. The tornado game is a game in which you sit on a chair. Right? It's a circular, right? It's a circular platform where you sit on one chair, and then you have your friends sit on other chairs, but the machine is circular, right? So it looks something like this. If you want to look from the machine from above, alright, so if you want to draw a plan view of the machine, right, it'd be a circle, right? It would be a circle. And if you want to look at, a side view of the machine, it would be something like this. So you would have this machine, right? So you'd have this here. You'd have one chair, okay, and then here you would have another chair, okay, and of course you have chairs everywhere, like a circle, okay, like a circle. But since I'm drawing it in 2D, only 2 chairs will be visible, right? So you'd be sitting in here, and your friend would be sitting in here, right? And if you want to look from above, this machine is rotating in a circular fashion, and the circle is of radius r, okay, and so you are here, which is which is you in this case, from the side view it's in here, and your friend is in here, right, which is represented by the two red dots in here. So this is you and your friend, okay, and the circle is rotating. As the circle is rotating, you know, it's rotating like this, okay, it's from the side view you can see it, it's rotating like this, okay, rotating, and the radius with, you know, it's with the radius r, okay, with the radius r. Now the point is, if there is a person in here, that is watching you guys rotate, okay, and this person is asked what would be the circumference of the circle, what would be the circumference of this circle, okay, from the perspective of an observer that is watching from the outside. He's not actually experiencing the rotation. He would say that from the perspective of this observer, okay, the circumference C is equal to 2 pi r, and this is the circumference as we know it, right? This is the circumference from the perspective of an observer that is seeing a circle on a flat surface. However, what Einstein observed is that from the perspective of the guys that are actually experiencing acceleration, that are actually experiencing rotation from the inside. So if you ask this guy to measure the circumference, if you ask this guy if you ask him what would be the circumference of the circumference of the circle for this guy is not gonna be 2 pi r. Is not gonna be 2 pi r, and the answer is because upon rotation, if you feel it, upon rotation there is a force that would be pushing you back, okay, on the chair. There would be some, you know, force due to rotation that would be pushing back, okay, away from the center of the circle, okay, and this force, okay, if you get, you know, if you want to measure the distance traveled, okay, the distance traveled upon rotation, because of this force, this will, you know, increase the circumference, because it would be harder for you to measure the whole circumference. Now please don't get me wrong, I'm not telling you that the circumference of a circle is not 2 pi r. All I'm saying is that the one that is actually experiencing acceleration, the one that's actually experiencing rotation, okay, in the tornado ride, is not experiencing a circle. Right? Because there is a force that is pulling you back while you are rotating. Go and try it, okay? If you go to the amusement park and, you know, try the tornado ride, you'd feel this force pushing, you know, on your back as you rotate. As you rotate, would be like this, okay? As you rotate, would be like this, and you know, the length, you know, becomes contracted as relative to the one that is measuring the length from the outside. And what this really means is that if you ask a person actually experiencing acceleration, actually experiencing rotation from the inside, from the inside of the tornado ride, it would require more length, okay, because there is a force that is, you know, pulling, you know, it's pushing you back, and it is preventing you from measuring the length. So the actual length measured inside the tornado ride is not going to be the length of a circle. It's going to be actually the length of a curve. And this goes back to the theory of special relativity, okay, the theory of special relativity, which is also Einstein's, and I might do a video explaining, you know, giving you a brief introduction of the special relativity as well, which came before the general theory of relativity, which generalized the special relativity to the gravitation. So the point is, acceleration can affect curvature. As you can see in here, acceleration can affect curvature, because from the point of view of the one under acceleration, meaning the one inside the tornado ride, okay, the curvature is not 2 pi r anymore. This is one. Two, as we explained earlier, acceleration can affect gravity, because if you leave a man with a scale to free fall under the acceleration of gravity, which is 9.81 meter per second squared, he would be weightless. The weight is gonna go to zero. So acceleration can indeed affect gravity. It can cancel out gravity, or it can create gravity. It can decrease it, can increase it, depending on the acceleration. So these two concepts led to the most important conclusion, which is gravity can be affected by curvature. Because if acceleration affects gravity and acceleration affects curvature, then there should be a relationship between gravity and curvature, and this led to an amazing discovery by Einstein, which gives an explanation of gravity, which explains the mechanism behind the gravitational force. And I'm going to explain this mechanism by using the following schematic. So suppose that you get, a rubber sheet. Okay, the sheet that you put on your tables, before you take dinner. Okay, it's a rubber sheet. Okay, so I'm gonna represent it in here like this. Okay, so this is a 3D rubber sheet like this. This is a rubber sheet. 3D means into the page. Okay, so like this. Okay, these are the stands of the rubber sheets. The ones that you see in restaurants. Okay, it's a rubber sheet that covers the table. Okay, so suppose that this is a rubber sheet. Okay, initially flat, and then here you have hollow space. You have hollow space under the sheet. For example, suppose that this is a rubber sheet like this. Okay, and you have nothing in here. Okay, this is a rubber sheet. Okay, now suppose you get a ball which represents the sun. Okay, suppose you get a ball which represents the sun and put it on the rubber sheet. So if you get a ball in here which represents the sun, right? So this is the sun. Okay, and you put it on the rubber sheet and you place it on the rubber sheet. What do you think will happen if if there is hollow space, if there is nothing below the rubber sheet, and I'm holding it from these sides, okay, from all of these sides, and it's circular. Okay, and what happens? What do you think will happen when I place a ball in the middle? When you place a ball in the middle after placement, what's gonna happen is that the sun is gonna occupy space. And the rubber sheet would look something like this. Okay, so instead of being flat, when you place the ball in the middle, because the sun has mass, because the ball has mass, what's gonna happen is that the rubber sheet will now look something like this. Okay, so the rubber sheet will now look something like this. Okay, it's gonna be curved. It's gonna be a curved surface. With the sun being in the middle, right? So if you place the sun in the middle of the rubber sheet is gonna deform. If the sun has, if the ball has enough mass, what's gonna happen is that you're gonna have curvatures from all angles, like this. So this is into the page, and from this, right, and from this, okay, from this side. Okay, see what I'm saying? So what I'm saying is you're gonna have curvatures. Okay, you're gonna have curvatures, and this would be in here the ball representing the sun. Okay, now if you get another ball which represents the earth, and give it a slide on the final shape of the rubber sheet in here. Okay, so of course in here you have the two stands that are holding the rubber sheet. Okay, so if you get a ball in here, okay, which represents the earth, and you slide it on this rubber sheet, what's gonna happen? The ball will start rotating about the sun, right? It starts rotating about the sun in orbits like this. And why is that? This is not because of the explanation that Newton provided. This is not because of the two masses being there and a force being exerted by these two masses. This is because the sun occupied space. It changed the fibers of space, and as a result, because the sun has a very high mass, it changed the space around it. And because of that, it allowed the earth to orbit around it. Look at the rubber sheet. It was flat. Let's consider this to be the universe or the space. It was flat. You get a ball with a very high mass, you put it on the rubber sheet. The rubber sheet is gonna deform like this, creating orbits. If you get the earth and you slide it along the rubber sheet, you are going to have orbits around the sun. And this is how curvature is related to gravity. Notice, it's not about the force. Okay, it's not about the force. It's about the structure of the space created by such a huge mass like the sun. Okay, so the sun has a very huge mass, and the earth as well. Okay, and the sun, because of its high mass, it deforms the space around it, creating these orbits. And due to these orbits, the earth is going to be able to rotate about the sun. Okay, so gravity as Einstein explained it, okay, gave a structure for the universe. It gave a structure for the behavior of the earth around the sun. Okay, before Einstein, gravity did not have a mechanism. Okay, did not have a mechanism. Although Newton succeeded in, relating the force between two masses with the formula that we explained in the beginning of the video, but he did not provide the mechanism, under which gravity occurs. After Einstein, after he connected the dots, after he found the relationship between acceleration and gravity, as we saw in the first principle. In the second principle, which is the second connection, we saw that he gave a connection between the acceleration and the curvature. He finally found that there is a connection between curvature and gravity, and this is the relationship between curvature and gravity. And from here, Albert Einstein concluded that objects with very high masses create warps. Okay, create warps in space, and these warps will modify the space around them, creating these shapes that you can see in front of you, which upon placement of objects, they will be able to rotate about these very high masses, such as the sun. Okay, so the sun in space, okay, creates these fibers that you cannot see, but you can visualize in here. Okay, these fibers, these warps, we call them. Okay, these warps will are the cause for why the earth moves around the sun, and the same principle in here applies in the case we need to understand the rotation of the moon around the earth in the same way, in the same exact way. So there's nothing to be said really. Albert Einstein is a real game changer. Alright guys, I am very glad you watched this video. I hope it was interesting, I hope it was beneficial. I'm not an expert on the subject. I got this information from the internet, from reading some books, reading some articles, understanding the theory of relativity. It's really interesting. It's really interesting to at least know what is what this theory is about. It has a wonderful equation. The mathematics is very complicated, but maybe you can see this see the equation corresponding to the general theory of relativity on the internet, and try to understand it more and more, and try to understand its implications, and one of its implications is the black hole. So I hope you enjoyed, and I will see you soon, hopefully in the next video. Thank you for watching, and